Hello everyone, welcome back to a physics lesson with me, Physics Michael. In today's video, we are going to explore how interference applies in an important and powerful tool in optics, diffraction gratings. We'll cover three key ideas: what diffraction gratings are, the interference equation for gratings, and how white light is dispersed into its colors through a grating. Let's get started. A diffraction grating is an optical device with a large number of very closely spaced parallel slits, often hundreds or even thousands of lines per millimeter. Just as we can see in the figure, this is a diffraction grating and it has 500 lines per millimeter, so we can calculate the separation between adjacent slits by 1 millimeter divided by 500, which is 10 times 10 to the power of negative 6 meters. When a beam of light shines through a diffraction grating, it behaves much like it does in the double-slit experiment, but with many more slits contributing. This creates sharp and bright interference patterns because the waves from all the slits combine constructively in very specific directions or angles. The bright spots have orders 0, 1, 2, 3, starting from the center spots to both sides, as shown in figure. Gratings are more precise than two slits, which makes them ideal for measuring wavelengths of light and analyzing spectra. So remember, a diffraction grating works by creating interference between light waves passing through many slits. The result is a set of well-defined bright spots called diffraction pattern. The bright spots in the diffraction grating pattern appear only when the waves from all the slits arrive in phase at a certain angle. So the path difference from adjacent slits must equal n lambda for each bright spot or maxima at different angles. Now let's consider the 0 order maxima first. 0 order maxima is right in the center point, so all rays through slits are parallel to each other for this direction, which means there is no path difference at 0 order. Then let's consider the first order maxima. As we can see in the diagram, the rays to the first order maxima all have an angle theta to the center line. So each ray from a slit travels longer distance than a ray from the next slit. By trigonometry, we can calculate the path difference between adjacent rays by the slit separation d times sine of theta, which must equal to 1 wavelength for the first order maxima. Hence, we get equation lambda equals d times sine theta for first order bright spot. Similarly, for the nth order maxima, the path difference between adjacent rays must equal to n lambda. So the equation for the nth order maxima of gratings is n times lambda equals d times sine theta, where n is the order of the maxima, lambda is the wavelength of light, d is the slit separation, which is the distance between adjacent slits, theta is the angle to the center line at which the bright fringe appears. By measuring the angle theta of the bright spots on the screen and knowing slit separation d, we can calculate the wavelength lambda of the light. This is how diffraction gratings are used in spectrometers to precisely identify wavelengths in spectra. Here's an example. Monochromatic light is incident normally on a diffraction grating have 300 lines per millimeter. The angle theta between the zeroth and first order maxima is measured by 10 degrees. Part A, calculate the wavelength of the incident light. Part B, calculate the angle theta 2 for the second order maxima. Part 3, calculate the angle theta 6 for the sixth order maxima. To solve this question, we need to calculate the separation d between adjacent slits in the gratings. Since the gratings have 300 lines per millimeter, so d equals 1 millimeter divided by 300, which equals 3.33 times 10 to the power of negative 6 meters. Then, by the equation n lambda equals d sine theta, we can calculate the wavelength by lambda equals d sine theta divided by n. Here n is 1. So lambda equals 3.33 times 10 to the power of negative 6 times sine 10 degrees, which equals 5.8 times 10 to the power of negative 7 meters. Next, let's calculate the angle for the second order. Using sine theta equals n lambda divided by d, we get sine theta equals 2 times 5.8 times 10 to the negative 7 divided by 3.33 times 10 to the negative 6, which equals 0.348. So, angle for the second order is 20.4 degrees. Similarly, we can use the same equation to calculate the angle for the sixth order. But the sine or angle of the sixth order is 1.05 which means there is no sixth-order maxima existed, since sine of an angle must be less than 1. Or we can say the maximum order in this situation is 5, and the maximum number of bright spots can be observed is 11. This is because there is a central bright spot in the center, with 5 bright spots on both sides of the center. Now, what happens when we shine white light through a diffraction grating? White light is a mixture of many wavelengths, from violet to red. Because the angle theta depends on wavelengths, each color gets its maxima at a different angle. So instead of a single bright spot, you get a spectrum, with violet diffracted least and red diffracted most. This effect is called dispersion, and the diffraction gratings are excellent tools for splitting white light into its component colors. Here's an example. White light is incident normally on a diffraction grating with a dispersion d of 2.000 times 10 to the negative 6 meters. The visible spectrum has wavelengths between 400 nanometers and 700 nanometers. Calculate the angle between the red and violet ends of the first-order spectrum. We need to calculate the diffraction angle of the violet end and the red end, respectively, using the diffraction equation n lambda equals d sine theta. For the violet end of the first order, sine theta equals the wavelength of violet end divided by the dispersion. Substituting the values, we get the angle of the violet end is 11.5 degrees. Similarly, we can calculate the angle of the red end using the equation and quantities, and we get the angle of the red end is 20.5 degrees. So the angle between the red end and the violet end is 20.5 minus 11.5, which equals 9 degrees. Now let's quickly summarize what we've learned today. A diffraction grating contains many closely spaced slits that causes interference of light. The grating equation is n lambda equals d sine theta, and it tells us the angles at which constructive interference occurs. When white light passes through a grating, it spreads into a spectrum of colors because each wavelength is diffracted at a different angle. This process is called dispersion. That's it for today's video on interference and diffraction gratings. Thanks for watching. I'm Physics Michael, and I will see you in the next video.